Welcome to a new video about controller realization. This is our example number 9. In this example, we will look at the active realization of a controller. In this case, we will look at the lag lead controller realization. So we will work out the calculation step by step to get to this specific circuit, and also do that with a simulation to verify our calculations. So let's look at our example. We have a design problem. We would like to design a physical electric circuit for the given lag lead controller that's shown here, and we would like to know what kind of a circuit will do the job to get this transfer function, and the LL is here the lag lead for short. Okay, let's look at the solution. There are many options, so let me start with a very general diagram. We have an input for this transfer function over the controller, lag lead controller, and there will be an output. But this lag lead controller is composed of several parts. It has a lag part and also a lead part. Those are definitely in it. But there will be also, if necessary, a gain stage. So this is then determined later if it's really required, and it depends on the value of the lag and the lead combination. So if the lag and the lead together has a gain of 1 exactly, then there is no gain required. But if the gain is different, then we need to add the gain that compensate that. So this together, whole thing, will be then making this lag lead controller. So we can say if we require a gain, and also the lag lead, of course, in this case, then the separate parts will then give you lag, the gain stage, and the lead stage. So we can say the transfer function of this each circuit will be then together with the product of the K, the lag, and the lead. So this is then the circuit transfer function, which is then called H. Now for each part we can now use a circuit realization, and this is what we have discussed in the previous examples about the lag. This is the circuit, the passive circuit. There's also a gain stage, can be in this case with a non-inverting amplifier configuration, and we have a lead stage, which is then this one. And if you now connect them together, we can get your complete circuit. Now the lag transfer function using this part is shown here. So you see the R1, R2 and the capacitor C1. The lead transfer function is here with the R3 and the C2 and R4. That's shown here. And we have also the gain stage, which is then the transfer function of the non-inverting amplifier, which is then shown here. That is the very basic formula. So connecting these three subparts, we can get this complete circuit. And that is the circuit we would like to design. So there are a number of unknowns. So we'd like to determine that. So let's move on and bring them all together. And this is the circuit we need to design. There are a lot of parameters as said we need to determine. These are the transfer functions for each stage in this circuit. This is the lag part as said before, and this is the gain stage, and this is the given here the lead part. So if I now multiply as said here the transfer functions of these three stages, so the lag, the gain, and the lead as shown here, then we have this transfer function completely. Now we can bring the terms here in the numerator together and also denominator together, then you will have this expression. Now I already given some colors here, and we can compare that using these colors with the transfer function of the controller as given and the transfer function of the circuit. So we see the red one is here, the blue one is here, and the green one is there, and also the pink one. So if I continue, I can say the following: compare the terms in the circuit transfer function with the given lag lead transfer function here. So what we see, as said, the 0.08 will be then 1 over R2 times C1, and a 2.5 here will be then 1 over R3 times C2, so that's the next one. The 0.001 must be 1 over the R1 plus R2 times C1, that's shown here. And the 40 here in pink is then 1 over the R3 times C2 plus 1 over R4 times C2. That's shown all here. In addition, we know that there is here a coefficient which is just 1, and this whole thing here as the parameter must be also 1. That means this is completely 1. So let's then take these together. What we see is actually we have 1, 2, 3, 4, 5 equations. And how many unknowns do we have? Let's see the circuit. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 unknowns and only 5 equations. So we need to really select 3 of them. So that is actually what we need to do. So next, collect now the equations we had. These are the equations. And let's now start with the first stage, part 1, the lag controller stage, this one. So for that we use these 2 equations. So let's say that the following, if we have freedom to choose something, let's then select the C1 because that's more practical to also have it in the lab. So 100 microfarad is a nice value for the capacitor C1. Then we can use this equation to get the R2. So 1 over the 0.08 times the C1 and you will get 125 kilo ohms. So that's for the first thing. Now moving on with that one, because since we know the R2 and also the C1 already selected, we can calculate now using this formula and also rewrite it in this form. When you rewrite this such that you express R1 in terms of the rest of the parameters, you will get this. And when you calculate now using the selected and also calculated value here, you will get 9.875 mega ohms. So that is R1. So we have now the values for the lag controller circuit. Okay. Part 2 is the gain stage, this one. Now we already said that this must be 1. So we can use that, and let's first calculate this R2 over R1 plus R2 because we know the values of these 2 resistors, and that will give us 1 over 80 exactly. So that means this times 1 over 80 must be 1. So let's write it down. That's shown here. Now in order to get here 1, that means actually this here must be 80. So 80 is equal to 1 plus RF over RM. Now, in here is also freedom, so you can make a ratio here in order to get that 80. So you can say RM is, for example, 1 kilo ohm, just you can select one, so another selection. So, and then you can say RF will be then 80 minus 1 times the value we have chosen for the RM, and you get now in this case 79 kilo ohms. So also the gain stage is done. Now the remaining 3 components. So the part 3. Let's also summarize here the values we have so far. So these 5 values. Now lead controller transfer function. Also here selection required because we get 2 equations only and we have 3 unknowns. So let's select again the capacitor C2 and also 100 microfarad is good. Then we get the following using this formula because R3 is then 1 over the 2.5 times C2. And when you do the calculation you get 4 kilo ohms exactly. Now since we know the R3 and actually also this ratio 1 over R3 times C2, we can say the following is 40 is equal to this equation. So we can say this is also actually the 2.5. That means 1 over R4 times C2 is actually 37.5. So we can calculate now R4, the remaining components. 1 over the 37.5 times C2, we know C2, just calculate this in this formula and you get 266.7 approximately ohms. So that means we have now everything. So we can also take that here, so we make list and these are the 8 unknown component values we have determined right now. And this is the circuit, so we can see here the complete circuit as drawing in the SPICE simulator. So we can see the first stage, which is the lag controller stage. This is the gain stage, K, and this is the lead controller circuit. You can see the values and all of them are here. It's actually 266.67, so just round it off to 266.7. Okay, let's now look at the simulation results, because these are also very important. And we have now here the frequency response. So let's see that. This is the body plot. We see the gain here and the phase together. First thing is the low frequency gain, which is here 5. And that is determined by looking at the transfer function here by substituting for the S0. If you do that here, you will get 0.08 times 2.5 over 0.001 times 40, because the S is all 0. It will be exactly 5. And if you then do 20 log of that value, you get 13.8 98 dBs, which is exactly as here. So that is verified. Let's also do the other extreme, which is the high frequency gain, which says here 0 dB. Now when you go with the S to infinity, so very large values, this will be a very large times very large over again two very large values. So you get the product of two large values. So in the limit definition, there will be just 1. So that will get a high frequency gain of 1, and 20 log of 1 is indeed 0 dB. So again, verified. In addition, you see here the lag pole that is in the frequency 159.50 microhertz, and if you convert that, it will be 1 milliradians per second, which is 0.001. So that's correct. The lag 0 is here at approximately 0.0753 radians per second, which is 0.08, which should be actually 8. So this is a little bit smaller. So that is the small error here. The lead 0 here is 2.666 radians per second. It had to be 2.5, also very small error here. And there's also the lead pole here, which is 39.85 radians per second, and also very close to actually 40. So there are small errors here, but still very close to what we actually required. And the determination of the pole and the zeros here is done in this format. You look at the low frequency gain, for example, here, that is the 13.98. You go down by 3.01 dB and you determine the frequency. You look at your minimum value here, so that is in this case minus 23.81 dB. You go up by 3 dB and you determine the frequency. You go also up by 3 dB and you determine your frequency. You also look at your high frequency gain, which is 0 dB. You go down by 3 dB and you also determine then the pole. So the pole and the zeros are determined in this fashion. So we have a first pole, then the 0, then again a 0, and then again a pole, and then the complete thing. And this is the phase. You can see also the maximum and the minimum phase contributions for this specific circuit. Alright guys, this is our active realization of the lag lead controller transfer function using this circuit. And we have seen that the circuit using the 3 stages, the lag and the gain stage and also the lead controller together in cascaded format will produce this transfer function. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. See you next time in another video. Take care.